Hello and welcome to this new example on Otto cycle. So we have a gas engine working on Otto cycle that has a cylinder bore of 200 millimeters and a stroke length of 250 millimeters. So B is equal to 200 millimeters and the stroke S is equal to 250 millimeters. The clearance volume, so the minimum volume, is 1570 centimeter cube. The pressure and temperature at the beginning of compression are 1 bar and 27 degrees Celsius. So this means that the pressure at state 1 is equal to 1 bar and the temperature T1 is 27 degrees Celsius or 300 Kelvin. Now let's draw the PV diagram for this cycle. So we have the pressure on the y-axis and the specific volume on the x-axis. So starting from state 1, where the piston is located at the bottom dead center, we have isentropic compression to state 2. So during this process, PV to power gamma is equal to a constant. And state 2 is the state where the piston reaches the top dead center. Then we have constant volume heat addition, since this is an Otto cycle, to state 3, then followed by isentropic expansion to state 4. So during this process also we have PV to power gamma is equal to a constant. Then we have constant volume heat rejection back to state 1. So the maximum temperature of the cycle is 1400 degrees Celsius. And as we said, the maximum temperature occurs at state 3 after the heat addition process is completed. So we can say that T3 is 1400 degrees Celsius, equivalent to 1673 Kelvin. Now we need to determine the pressure and temperature at all state points, the indicated thermal efficiency, the work done, and the indicated mean effective pressure, the IMEP. Also, we need to calculate the indicated power if the number of working cycles per minute is 500. So this engine will produce 500 working cycles per minute. So for this number of cycles, we need to determine the indicated power. Now given for air, the specific heat at constant volume CV is 0.718 kilojoule per kilogram Kelvin, and the gas constant for air is 0.287 kilojoule per kilogram Kelvin. So let's start with state 2. So we know the pressure and temperature at state 1. So let's start at state 2. So to calculate the pressure at state 2, we know that P2 divided by P1 is equal to R to power gamma. So to calculate the pressure at state 2, we need first to find the compression ratio R. So R is equal to the maximum volume V1 divided by the minimum volume, which is the clearance volume VC. So here the clearance volume is the volume at state 2, and the maximum volume is equal to the clearance volume plus the displacement volume VD. So let's calculate first the displacement volume. Of course, for one cylinder, this will be equal to pi over 4 B square S. So pi over 4 multiplied by the bore square multiplied by the stroke. So the displacement volume will be equal to 7.85 times 10 to power minus 3 meter cube. So R is V1. So V1, as we said, is the clearance volume plus the displacement volume divided by the clearance volume. So the clearance volume is given to be 1570 centimeter cube. So we want to convert it to meter cube. So 1570 times 10 to power minus 6 meter cube plus the displacement volume times 10 to power minus 3 divided by the clearance volume 1570 times 10 to power minus 6. So the compression ratio in this case will be equal to 6. Now P2 will be equal to P1 into R to power gamma. So here we know the specific heat at constant volume and the gas constant, but we don't know the specific heat capacity ratio gamma. So we say that gamma is a ratio of Cp to Cv. So we know Cv, but we don't know Cp. However, for an ideal gas, there is a relationship between Cp, Cv, and R. So Cp for an ideal gas is equal to Cv plus R. So always the specific heat at constant pressure is larger than the specific heat at constant volume by an amount equal to R for an ideal gas. Of course, if we want to know the meaning of the specific heat, so the specific heat is the energy required to raise the temperature of 1 kilogram of ideal gas by 1 Kelvin. So of course, this energy during a process at constant pressure will be larger than the energy during a process at constant volume. So it is much more easier to raise the temperature of an ideal gas if we have a constant volume process than a constant pressure process. So that's why Cp is greater than Cv by an amount equal to R. Now Cp in this case will be equal to Cv 0.718 plus R 0.287. So this will be equal to 1.005 kilojoule per kilogram Kelvin. Now gamma in this case will be 1.005 divided by Cv, which is 0.718, so approximately will be equal to 1.4. So now we know R and gamma, we can calculate the pressure at state 2. So P2 is P1, which is 1 bar times 6 to power 1.4. So P2 in this case will be equal to 12.286 bar. Now for the temperature, so T2 divided by T1 is R to power gamma minus 1. So T2 will be equal to T1. So T1 is 300 Kelvin. So please be careful when using this equation is to always put the temperature in Kelvin and not in degrees Celsius. So if you compute T2 by using T1 in degrees Celsius, you will obtain wrong results. Okay, so always convert the temperatures to Kelvin before using these equations. So T2 is 300 times R 6 to power gamma minus 1 to power 0.4. So this will be equal to 614.3 Kelvin. Now state 3. We know the temperature at state 3 equal to 1673 Kelvin. Now we need to calculate the pressure. So applying the ideal gas law at state 3, we know that P3 V3 is RT3. And also applying the ideal gas law at state 2, we know that P2 V2 is RT2. And let's divide these two equations. So since this is a constant volume heat addition process, we can simplify V3 with V2 and also R with R. So we'll have P3 divided by P2 is equal to T3 divided by T2. So P3 is P2, which is 12.286 bar multiplied by T3, 1673 divided by T2, 614.3. So P3 will be equal to 33.46 bar. Now state 4, we have isentropic expansion. So we know that P4 divided by P3 will be equal to 1 over R to power gamma. Of course, since P4 is less than P3, so that's why we have 1 over R and not R to power gamma. Now P4 will be equal to P3, 33.46 multiplied by 1 over 6 to power 1.4. So P4 will be equal to 2.723 bar. Now for the temperature, we have T4 divided by T3 equal to 1 over R to power gamma minus 1. So T4 is T3 1673 multiplied by 1 over 6 to power 0.4. So T4 will be equal to 817.025 Kelvin. So now we know all the temperatures and pressures at all state points. Let's calculate the indicated thermal efficiency. So for an Otto cycle, as we saw before, that the indicated thermal efficiency is function of compression ratio only. So we know the compression ratio, we can calculate the indicated thermal efficiency. So for an Otto cycle, eta is simply 1 minus 1 over R to power gamma minus 1. So 1 minus 1 over 6 to power 0.4. So this will be equal 0.512. Now we need to calculate the indicated work, W cycle. So W cycle is simply the thermal efficiency, the indicated thermal efficiency multiplied by the heat input. And the heat input is during the process from state 2 to state 3. So eta times Qn. Qn is the mass of air inside the cylinder multiplied by the specific heat at constant volume multiplied by the temperature difference T3 minus T2. So to calculate the W cycle, we need to find the total mass of air inside the cylinder. So if, for example, we apply the ideal gas law at state 1, we can say that P1 V1, so V1 here is the total volume, not the specific volume. So this will be equal to the mass of air into R into T1. So M is simply P1 V1 divided by R T1. So the pressure at state 1 is 1 bar, equivalent to 10 to power 5 Pascal, multiplied by the volume V1, which is the clearance volume, 1570 times 10 to power minus 6 meter cube, plus the displacement volume. So we have already calculated the displacement volume, which is 7.85 times 10 to power minus 3, plus 7.85 times 10 to power minus 3 meter cube, divided by R. So R is given to be 0.287 kilojoule. However, since we put the pressure in Pascal, we need to put R in joule. So it is 287 joule per kilogram Kelvin multiplied by the temperature T1, which is 300 Kelvin. So the mass of air will be 0.01094 kilogram. So the indicated work, W cycle, will be eta 0.512 multiplied by the mass 0.01094 multiplied by the specific heat at constant volume. So the specific heat at constant volume is 0.718 multiplied by the maximum temperature 1673 minus the temperature at state 2. So the temperature at state 2 is 614.3. So the indicated work in this case will be equal to 4.26 kilojoule. So of course this is in kilojoule since we put the specific heat in kilojoule per kilogram Kelvin. Now we need to calculate the indicated mean effective pressure, IMEP. So IMEP is the indicated work divided by the displacement volume, of course for one cylinder. So 4.26 divided by the displacement volume, which is 7.85 times 10 to power minus 3. So the IMEP in this case will be equal to 542.4 kilopascal. Of course in kilopascal since the work here is in kilojoule. And if we want to convert from kilopascal to bar, we need to divide by 100. So this will be 5.42 bar. Now the last part of this problem would be to calculate the indicated power if the total number of working cycles per minute is 500. So we need to calculate the indicated power, W dot indicated. So this will be equal to W cycle, which is 4.26 kilojoule. So W indicated or W cycle is the work executed per one cycle per one cylinder. So to obtain the indicated power, we need to multiply W cycle by the total number of cycles executed per second. So given in the problem, we have 500 working cycles executed per minute. So we multiply by 500 cycles per minute. So to convert to cycle per second, we multiply by 1 minute and divide by 60 seconds. So we can simplify minute with minute, cycle with cycle, and we will obtain kilojoule per second, which is equivalent to 1 kilowatt. So we'll obtain the units of kilowatt per one cylinder. So W dot I will be equal to 35.5 kilowatt per cylinder. So this is the indicated power produced by one cylinder. And of course, if we have multi-cylinder engines, we need to multiply by the total number of cylinders in order to obtain the total indicated power produced by all the cylinders in the engine.